This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Topic 12 of Week 5 and the final lesson of the course: refrigeration cycles and heat pumps. We run the power cycle backwards: 4 components, 4 state points on a pH diagram. Then turn enthalpy differences into a coefficient of performance and a tonnage. One worked R134A cycle ties it all together. Start with the big idea. A heat engine takes heat in hot and produces work. A refrigeration cycle is that cycle reversed. You spend compressor work to pump heat from cold up to warm. Call it a refrigerator when you care about the heat pulled out of the cold space, and a heat pump when you care about the heat delivered to the warm space. Same hardware, different output of interest. The workhorse is the vapor compression cycle: boil, compress, condense, throttle, and every exam problem is a slice of those 4 steps. 4 components, 4 state points. Compressor 1 to 2, isentropic compression, saturated vapor in, superheated out. Work goes in, H2 minus H1. Condenser 2 to 3, constant pressure, the vapor rejects heat and condenses to saturated liquid. Expansion valve 3 to 4, isenthalpic throttling, enthalpy is conserved, H4 equals H3. Evaporator 4 to 1, the mixture boils back to saturated vapor, absorbing the load. Watch the valve. It is isenthalpic, not isentropic. A turbine would conserve entropy. A throttle just drops pressure and entropy rises. Use H4 equals H3 every single time. Refrigeration cycles live on a pressure enthalpy diagram, not a TS diagram, because every energy term becomes a simple horizontal gap. 2 pressure lines, the low evaporator and the high condenser. The bottom segment, 4 to 1, has a width equal to the refrigeration effect. The top segment, 1 to 2, leans right, and its width is the compressor work. And 3 to 4 is a vertical drop, because throttling holds enthalpy fixed. The saturation dome sits underneath, liquid on the left, vapor on the right. That vertical throttle line is why this chart is the working tool. You read H4 by dropping straight down from state 3. The variable table. Just 4 enthalpies drive everything. State 1, saturated vapor at the evaporator pressure. Read Hg from the table. State 3, saturated liquid at the condenser pressure. Read HF. State 4 equals state 3 by throttling. And state 2, the superheated discharge. Read off the pH chart by following the constant entropy line up to the condenser pressure, because there is no superheated R134A table to interpolate. 3 table lookups, 1 chart read, 1 equality. The whole cycle falls out of that. Now the score. The coefficient of performance is what you want over what you pay, both per pound of refrigerant. For a refrigerator, it is the refrigeration effect, H1 minus H4, over the compressor work, H2 minus H1. The numerator is the heat absorbed in the evaporator. The denominator is the work in. Unlike a heat engine efficiency, COP is not capped at 1. A good refrigerator moves several units of heat per unit of work. 2 to 4 for a household fridge, 4 to 6 for a commercial chiller. The reversed Carnot sealing uses absolute temperatures, cold over the temperature difference. Flip to heating. Now the prize is QH, the heat dumped in the condenser over the same compressor work. An energy balance on the loop says QH equals QL plus the work. So divide through, and you get the identity the exam loves. The heat pump COP is the refrigerator COP plus exactly 1. That plus 1 is exact, not an approximation. And because it is always greater than 1, a heat pump always beats resistance heating. Every unit of work delivers more than a unit of heat. Capacity is rated in tons, and 1 ton is 12,000 BTU per hour. The ideal cycle is the starting line. 3 real effects move it. Superheat at the evaporator exit. The vapor leaves a few degrees above saturation, so no liquid slugs the compressor. It nudges state 1 up. Subcooling at the condenser exit. The liquid leaves below saturation, dropping H3. And since H4 equals H3, the refrigeration effect grows. Subcooling is free capacity. And compressor inefficiency. Real compression is not isentropic, so the actual work exceeds ideal, and COP falls. Refrigerant choice sets the pressures. R134A for automotive and commercial, R410A for residential air conditioning and heat pumps, running well above the old R22. Worked. Problem. An ideal R34A vapor compression cycle between a saturated evaporator at 0 Fahrenheit and a saturated condenser at 100 Fahrenheit. Trace the loop. The compressor lifts low-pressure vapor at state 1 to high pressure at state 2. The condenser rejects heat and leaves saturated liquid at state 3. The expansion valve throttles to state 4. And the evaporator absorbs the refrigeration load, returning saturated vapor at state 1. On the pressure enthalpy chart, the cycle is a rectangle. Evaporation along the bottom, compression up the right, condensation across the top, and a constant enthalpy throttle straight down the left. From the tables, State 1, saturated vapor, enthalpy 103.16. State 3, saturated liquid, 45.16. State 4 equals State 3 by throttling. And State 2, following constant entropy up to the condenser pressure, about 120. Find the refrigeration effect, the compressor work, both coefficients of performance, and the mass flow for a 5-ton load. Now just subtract enthalpies. Refrigeration effect, H1 minus H4, 58 BTU per pound. Compressor work, H2 minus H1, 16.8. Heat rejected, H2 minus H3, 74.8. Check the loop balance, QH equals QL plus work, 74.8 equals 58 plus 16.8. It closes exactly. No integration, no specific heat. The whole job is bookkeeping the 4 states, especially H4 equals H3. Coefficients of performance fall straight out. The refrigerator COP is 58 over 16.8, about 3.4. The heat pump COP is that plus 1, about 4.4, and it matches 74.8 over 16.8 independently, so the cycle checks. Now size the flow for 5 tons. 5 times 12,000 is 60,000 BTU per hour. Divide by the refrigeration effect, 58, and the mass flow is about 1,035 pounds per hour. Multiply that flow by the compressor work, and the power is about 17,400 BTU per hour, roughly 6.8 horsepower or 5.1 kilowatts. 4 traps. 1. Throttling is isenthalpic, not isentropic. The valve holds H4 equals H3. Assume constant entropy, and you have assumed a turbine. Wrong device, wrong answer. 2. COP is not capped at 1. It is heat over work, and 3 or 4 is normal. Reaching for a number below 1 because efficiency can't beat 100% is the classic blunder. 3. Don't forget the plus 1 for heat pump mode. It is exact, so just add 1. 4. Botching the ton. 1 ton is 12,000 BTU per hour, not per minute. Convert tonnage to BTU per hour before dividing by an enthalpy difference. Bookmark the refrigeration pages. The cycle layout, compressor, condenser, valve, evaporator, with H4 equals H3 at the valve. The refrigeration effect and the compressor work as mass flow times an enthalpy gap. The 2 coefficients of performance with the plus 1 identity. The tonnage, 12,000 BTU per hour, and the R134A chart and saturated property table, plus the refrigerant comparison. Fold the corners on the COP page and the property table. You will reach for both on every refrigeration question. That closes week 5. You now own the reverse cycle. 4 components, 4 enthalpies. The refrigerator COP, the heat pump plus 1, and tons at 12,000 BTU per hour. Step back and see the whole week. Rankine and regenerative power cycles, boilers and turbines, condensers and cooling towers, Brayton gas turbines, combustion, internal combustion engines, and now refrigeration and heat pumps. Together, that is the energy and power systems block, the largest single slice of the exam. The thread never changes. Pin the states, take the enthalpy differences, respect the conventions. Work refrigeration problems until the R134A table and the vertical throttle line feel automatic. Well done finishing week 5.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.